Great. Thank you very much for having me here as a part of this program. So today I'm going to tell you about some, kind of experiments which have that flavor of transport has not been talked about in this meeting thus far, but I'll try to make it simple and interesting for the broad audience. So we do experiments with systems that have Berry curvature, and one of the systems that I will describe is twisted layers of graphene. So I'm sure many of you would have heard about it because it's been in sort of news of late quite a bit. And I'll tell you about a transport which is a transport of Wally degree of freedom. So you should think about Wally transport as analogous to spin transport, where Wally is another degree of freedom that exists in these systems, particularly honeycomb lattices. So I'll try to explain this and demystify as we go along. As I mentioned earlier, if you have any questions, please don't hesitate to interrupt and ask the question. Okay, so we are grateful for the fundings that make this experiments possible. So we get generous funding support from Department of Atomic Energy and Department of Science and Technology of India, and that really makes these experiments possible. I want to acknowledge my collaborators, actually the people who do the work. The two PhD students have led the work, are Pratap and Subhajit. Both of them have led these experiments to an interesting stage. We collaborate with theorists at TIFR and in University of Seoul, and some of the experimental materials that we use, actually a critical one, hexagonal boron nitride, and I'll try to explain briefly, is actually made by these two gentlemen, Dr. Taniguchi and Watanabe in NIMS, Japan. So all these experiments are possible because of my collaborators, and I kind of give a talk on their behalf effectively. So let me present a brief outline of my talk. So I'm just to make it accessible for people who are not in this field. I'll try to give a quick 2 or 3 slides introduction to Berry physics, and then I'll try to make connection to solid state systems. Particularly, I will focus on on asking this question: why systems like graphene or 3 layers of graphene or 2 layers of graphene are interesting, and where does the twisting come in, and how that really helps uncover interesting physics. And then I'll talk about sort of the key part of my talk will focus on a particular kind of a twisted structure of graphene, which is bilayer of graphene, 2 layers of graphene, twisted relative to another piece of which is bilayer, and there is a small angle of rotation in between, and that small angle is critical. So this system actually and its related structures have actually Berry curvature, and that Berry curvature is responsible for a lot of interesting physics, which features in topological sort of aspects of condensed matter. But it's sort of the main thing that drives this Wally current. So it you basically send charge current, and the Berry curvature in the system actually drives the current, a pure current of a kind of a Wally degree of freedom, which is analogous to spin. So that's sort of the physics that I'll talk about, and I'll summarize at the end. So this is my rough outline. So in electronic bands, we look at simple 2-band pictures. You look at electronic states inside the band. In certain kinds of bands, and I'll qualify that, these electronic band, sort of the wave function in the bands for these electron packets has a self-rotation. Okay, so when that self-rotation is there, under what condition will become clear in a minute. But this self-rotation has an important consequence on the motion of these sort of semi-classical perspective to the motion of these electrons moving around in a crystal. So we are talking about electrons in a regular solid. They might have some symmetries. They give rise to some bands, and in certain bands, these wave functions have self-rotation associated with it, and that kind of plays an important role. And I'll qualify which bands are these where this happens in a minute. So, if I want to write down semi-classical equations of motions for an electron in a solid, you can look at any textbook like Kittel or Ashraf or Mermin, whichever one you like. And you've seen up to some constants. I've kind of got rid of constants in front, but you can write down equations of motion for velocity, then gradient of the momentum. If you have a perpendicular magnetic field, then this is sort of the equation set of equations that we know very well from basic courses in solid state physics. Now, this is what you'll see in Kittel, at least the older editions. But turns out that in certain solids, the ones where the electrons has this kind of self-rotation associated with it, there is another physics that's happening. Is that because of this self-rotation of the electron wave function, there is a kind of deflection of these electrons to one side because of this. It's analogous to sort of a Magnus-like force. And the consequence of this is that there is another term which, Kittel and all of these books would normally not show. This actually plays an important role. And there is a kind of a connection between these two equations, and the structure is very similar. So this sort of operator does the job of a magnetic field, but in momentum space. It's the Berry curvature. Okay, so if Berry curvature is 0, which is the case for most materials, you don't have to worry about this term, and all the equations that you saw in Kittel or any of the older versions of the textbooks, this works well. But there are materials where the Berry curvature is non-zero, and that can lead to very interesting physics of deflection to one side just because of a non-zero Berry curvature in the system. Okay, so this physics plays a very important role. So naturally, you might say that when is it that this term of Berry curvature can come into play? What sort of materials in a broad guidance for observing this? And typically, Berry curvature is non-zero if inversion symmetry or time reversal symmetry is broken. Okay. Most of the fun experiments are when time reversal symmetry of the system is preserved, but inversion, which is sort of the symmetry of the crystal, is broken. Then one can hope to find situations where the Berry curvature is non-zero, and all of this physics of electrons having another component of velocity called the anomalous velocity. This term right here is an anomalous velocity because of the existence of this Berry curvature. Okay, so we know now that under certain conditions, when the Berry curvature is non-zero, the semi-classical wave function has this kind of self-rotation, and that gives rise to this anomalous velocity. Now, there is a lot of interesting physics that emanates out of this. When we look at bands, one looks at, let's say, for a simple case of two-dimensional solids, one has a band, and you look at a kind of a periodic structure in space. So you look at a Brillouin zone, and you invoke certain symmetries, which are, symmetries of the translational symmetries, and you can basically fold this, and this whole system, sort of the band, can start to have some properties, which is of you can quantify this Berry curvature if you do it over the whole brilliant zone, you can have some invariance of the system, which is the Chern number, and that leads to some interesting physics. When overall the time reversal symmetry is broken, you have a non-zero Chern number. Okay, so and this can lead to interesting consequences in the physics, and there is a lot of excitement about this in looking at properties of solids in general, but certainly two-dimensional solids. And one pictorial way to imagine the consequence of a Chern, non-zero Chern number is that you have a kind of a one-dimensional transport mode which lives at the boundary of the system, and this has a protection. No amount of disorder can actually obstruct the flow of this edge mode in the system. So the the yellow areas are insulating, but because the system has this non-zero Chern number, you will get these edge mode, which is sorry, which is analogous to the quantum Hall systems, if you are familiar with it. And an opposite Chern number, sign Chern number, would basically mean an edge mode which is going around in the opposite direction, and you could have situation like integral Chern numbers, which will include more and more edge modes, which go along, either have a different kind of circulation and will determine the sign. So a lot of these solids that I will talk about, two-dimensional solids, have these interesting properties that you can break inversion symmetry, or the system inherently has inversion symmetry broken. And you can also, under certain conditions, have non-zero Chern numbers. Okay, so this is, I won't talk about the physics related to the Chern numbers in today's, I'll kind of loosely refer to it towards the last slide, but most of the discussion will be the key role played by this Berry curvature, which plays an important role. So I sort of give you a very short introduction to the Berry physics insofar as what is needed to understand this particular talk. Now I'll sort of move to another aspect, which is, why is there this sudden interest in looking at few layers of graphene or few layers of two-dimensional materials? And the bottom line is there are many reasons. One is that in a cartoon view, you can think of the dispersion, which is the energy momentum relationship of the electronic bands, actually has some interesting properties. So for graphene, monolayer graphene, the energy momentum relationship is linear. And if you stack many layers, the energy momentum relationship actually becomes flat. And that's kind of at the heart of a lot of the interesting physics of correlations that one can see in these solids. By correlations, I mean states which manifest themselves because of the independent electron picture no longer is an accurate description, and electrons either will condense as Cooper pairs or you can have magnetism. So there are lots of interesting reasons why people are excited about these systems, because there are, there's a nice way to break symmetries in these solids. Either you can apply some fields like electric fields and break symmetry. And there are new avenues for engineering these bands. I told you some bands have interesting properties. Having relative layers twisted with respect to each other allows a completely new way to construct solids, which has not been exploited so much in the past. It has come to the fore in the last roughly, something like 5 to 10 years. And then I already explained that, the fact that the bands become flat basically says in a simple way that if you make the bands flat, that's like saying that the effective contribution of kinetic energy is getting suppressed, and any kind of electronic interactions start to become important and dominate, and you will see correlated states. And I already explained there's a possibility to see Chern bands. We won't talk too much about it. And that sort of connects to a very important aspect which excites people in this field, which is states which are non-abelian in nature, which have possible consequences on certain proposals for quantum computing, which are have some topological protection against error. So this is sort of a big picture motivation why people are interested in this. Sort of what I will talk about in this bands is this sort of engineering of these bands to give rise to interesting Berry curvature, which leads to this transport of Wally degree of freedom. So typical twisted structures look like this. So you have an inherent atomic lattice, but a relative twisting and an angle and the two lattice constants can determine another length scale in the system, which is the twist, kind of the Moiré pattern. And the name basically arises from if you take two mesh of even square mesh and you rotate, you will get a kind of a beating pattern. This is a spatial beating pattern, much like in sort of an interference that you would get in sound. Now, the electrons that are moving around in this composite solid will see a potential of the atoms which is there, but then again a modulation of that potential will happen at a longer length scale, typically of the order of 10 nanometers. And that is sort of the length scale that gives rise to these bands which have some interesting properties. And so one of the really remarkable discoveries was because of these bands, which are very, very flat, and I'll talk a little bit about it, you kind of quench the kinetic energy contribution, and you can realize systems which are superconducting, which naively are not expected to superconduct. For example, all carbon system, people did not imagine that it will superconduct, but people have demonstrated that in these flat bands, one can see superconductivity, and that superconductivity, although it's relatively low temperature, but it is shedding some new light into understanding of how one thinks about microscopic origin of superconductivity. Okay. So now some important aspects need to be sort of discovered or rather to understood to understand the details of the physics that takes place in these systems. So these are, graphene and its derivatives have a honeycomb structure, and so the momentum space looks like this. It's also a honeycomb, and if you calculate the dispersion of which is the energy as a function of momentum, you'll basically see for monolayer graphene 6 points where this upper band of electrons meets the lower band, and they're degenerate at precise 6 points, which is at the corners of this hexagon. And something because of the original symmetry of the honeycomb lattice, it turns out that these two neighboring touching points are actually not equivalent at all. They have fundamentally different character, and one of the important is that the chirality associated with this two points in K space, they are very different. So what ends up happening is that in the physics of graphene world, you look at an effective low energy Hamiltonian, you kind of look at only energies which are close to this point, which is the Fermi energy. And these two K points are called valleys, and the electron has either belongs to one valley or the other. So just like it has either spin up or spin down, it has another degree of freedom in these solids, which is the valley degree of freedom. when you twist them, you actually, a real space twist also results in a twist in the momentum space, in the K space of these solids, and you have another Brillouin zone called the mini Brillouin zone, which is the Brillouin zone associated with, because of this modulation at a length scale of about 10 nanometers. And that's sort of where all the interesting properties of these solids can be understood. So the way to imagine how these flat bands arise, so you imagine a sort of a view of these are like cones. So when I rotate the two lattices relative to each other, I basically, in K space also, I have a, let's say, Dirac cone and another Dirac cone of the two layers. They are rotated by or shifted by some K vector, which is a function of the rotation angle. Then, because electrons are hopping between the two layers, these two bands are not independent, but there is hybridized, and they give rise to hybridization like this. And so you can already see that because of the two layers sitting on top of each other and electron hopping back and forth, you get these new bands which were not there. And under certain conditions where when the tunneling rate across between the two layers and across the two Moiré unit cells is the same, you get extremely flat bands. These are the flat bands where the electronic properties are interesting. But what will be the focus of today's sort of talk is that there are these gaps which have interesting properties which will have Berry curvature, and I'll talk about it as well. So just the act of relative twisting between them gives rise to a modification in the original electronic properties, which can actually be engineered in the sense there is complete tunability in terms of the angle of the relative rotation. Now, so this is actually a very convenient system to vary energies relative to some other energy scale in the system to see interesting physics. So, so overall, as I said, the system has two degrees of freedom or degeneracy of 2 because of spin, spin up and spin down electrons, and another is this 2 Valley degree of freedom. So a total degeneracy in the system is a degeneracy of 4. Okay, somebody has a question.
Is Surendra Pradhan.
Yeah.
Yeah, Mandar sir, am I audible?
Yes, please.
Yeah, I was just curious to know that since you have talked about this Berry curvature, so I was just trying to understand that can we calculate this Berry curvature as well as these char numbers in case of zigzag graphene nanoribbons as well?
Okay. If you have a model for them, it can certainly be calculated. I have to think a little bit more, but it's calculable. It's not a problem. You can calculate it for any structure and ask whether it has any non-trivial interesting Berry curvature, and if it's there, then where does it live?
Yeah, so we are able to calculate the band structure in that case actually.
It should be possible. Maybe we should talk about it afterwards. You can send me an email or something. It's possible. I mean, these methods are well established. I'm not an theorist, but these are relatively straightforward calculations to do once you have set up the system. Okay.
Okay. Thank you.
All right. All right. So since I'm an experimentalist, some of you might be wondering, how does one realize something which is relatively rotated, 2 layers of any material which is rotated relative to each other by something like 1 degree, and the way to do it is to the only definitive reliable way is to take one sheet of graphene and kind of cut it into 2 pieces. So these two are completely the same mother crystal. So you know they are aligned. So you cut one. I won't go into too much detail, but you pick up one. It's possible to do these manipulation. You pick up one layer and then you rotate the stage on which the remaining pieces, and then you actually assemble them one by one. It's kind of the assembly is analogous to in a sort of projects that one would imagine in a handicraft class for students in grade school. But it's complex and it's hard to do in reality for something which is only 1 atom thick. I just want to give you a flavor. And we also follow something similar, but we have our own different technique to do it. But the philosophy is still the same. You take 1 layer or 2 layers of graphene and you cut it precisely, and then you pick up 1 layer and another layer and assemble this sort of a Lego composite structure. So I hope I gave you a flavor of why these kind of materials are interesting and how one makes these kind of structures. I won't go into too much technical detail about it here because of time, but if you have questions, you can ask me at the end or you can email me. Okay, so now one of the things that is, as I told you, interesting about these layered materials like graphene or its family is that you can break some symmetries which lead to a band structure which is tunable. So for example, if you just take 2 layers of graphene, so monolayer graphene is a semi-metal, as I showed you in the cartoon. It basically has conduction band and valence band meeting in a conical shape. But if you take 2 layers of graphene, because of the hybridization, the resultant bands look like this. And it's a semi-metal, but if you apply a perpendicular electric field, it actually becomes a semiconductor where a gap will open up in the energy spectrum, which is tunable by the perpendicular electric field that you have applied, okay? And as you increase the magnitude of the electric field, you break the inversion symmetry of this bilayer and you open up a gap. So in case of inversion symmetry, existence of inversion symmetry in monolayer graphene ensures that it is a gapless system. Same thing for bilayer graphene, but if you break the inversion symmetry by applying a perpendicular electric field, you can open up a gap. So now this offers an opportunity to make more complex structures or solids, which is the system of our choice, which is twisted double bilayer graphene, which is basically bilayer graphene and another bilayer graphene twisted relative to each other. So you might say, why should one do that? Because if you can make just monolayer graphene on top of each other with a twist, then what's the advantage? The advantage is this, that if you apply an electric field, you can in situ, while doing the experiment, you can tune the band structure. This cannot be done very often in solid state physics. It's like tuning the energy level spectrum by an electrical knob, which is very convenient. So that's the reason we use the system. It gives rise to flat bands, which are completely tunable with electric field, and that's why we use them. So there have been some experiments where people have probed this physics of electronic correlations. I will not spend too much detail, but in case in it, what happens is if you have a band and you fill it exactly halfway because of a kind of a Stoner criterion being satisfied, what can happen is that the band spontaneously splits up into 2 bands because it's actually energetically favorable for electrons to lower their energy because of some interaction between the electrons. And so people have been able to explore that because the width of these bands is comparable to the interaction energy. So it's possible to see this physics of interaction, which is typically hard to see. And so people have explored this. Our focus is more to look at some non-trivial topological properties of the band. So that's what we will focus on in the remaining part of my talk, which is in the next 25 minutes or so. So the cartoon of the devices looks something like this, and this is an optical microscope. So that they're basically a few microns, long and wide devices. And these are electrical connections which are made to these by lithographic processes, which is basically techniques developed from semiconductor fabrication. So once you do this, you can actually start to measure its electrical properties. So what you see here is measurements on this structure of bilayer relatively rotated with respect to each other by something like 1.2 degrees. And we send current, measure voltages, convert it into resistances. And what you see here is numbers plotted in a color scale to visualize the large data set. So it's basically a bunch of numbers in terms of two parameters. One is the density of charge carriers in this system, and other is the perpendicular electric field. This is possible because we have typically two electrostatic gates, which is a gate below and another gate on top. So you apply voltage here and a voltage here, and that allows us to tune a density and electric field. That parameter space of density and electric field is basically some linear combination of the two voltages. So it's a kind of a rotation in the parameter space, but suffices to say that what you see is a system where you have low resistance, which is metal-like, and you see these sharp, large resistances, which are insulating gaps in the system. So it behaves like a system with semiconducting or a metallic system, depending on what value of density you have applied in electric field. It'll become clear in a minute. So if I take slices of the data, the way to think about it is if I apply no electric field in the system, I have two sets of flat bands, and my effectively cartoon description of the electronic solid looks like this. This is energy of the system, and this is density of states, which tells you how many states are available. And as you apply electric field, you will move one of the flat band relative to another, and you will start to open up a gap in the electronic spectrum. If you apply more voltage, it will be a bigger gap. And eventually, the flat bands will merge with bands which live at higher energy. So you won't really have any flat bands. So just to give you a sense, the flat bands have bands which a bandwidth of about 10 milli-electron volt. Okay, so room temperature is about 25 milli-electron volts. So these bands are at low temperatures are quite narrow, and they're comparable to the electronic interaction energy scale, again, of the order of few MeV. And these experiments are done typically at low temperatures, down to these experiments that I'll talk about are at tens of Kelvin or down to about 1.4 Kelvin. So what happens is that, you have these bands, and you can calculate different quantities like the Chern number of the flat band. These are, just to be sure, these are Valley Chern numbers, because overall the system does not break time reversal symmetry. So you don't have non-zero Chern numbers, but you have two valleys of the electron bands. K prime have opposite Chern numbers. So this is just a Valley Chern number. So what you see is that applying an electric field between them can endow some non-trivial topological properties to these bands. Okay, and if you look at the sort of the Berry curvature, this is a plot of Berry curvature in the K space. So it has a very complex but understandable structure, and it's not zero. Even if the total Chern number is zero, the Berry curvature is actually not uniformly zero. So there's a structure which depends on the which reflects the symmetry of the original lattice. And so the fact that it has non-zero Chern number and non-zero Berry curvature automatically leads to interesting physics. And that's what we study in our experiments. So the cartoon way to think about it is you have some flat bands, you have some dispersing bands, at high energies, but between these gaps of these flat bands, you have a Berry curvature. So if the electron lives in this band, it will feel the Berry curvature trying to deflect it to one side. Okay, and these hotspots will lead to the flow of this valley degree of freedom that I have mentioned earlier. Okay, so how does it work? So the typical geometry of these devices is like this. You have a channel where this layers of graphene are there, and this is a semi-classical equation which reflects the existence of the Berry curvature. So one of the properties of this system is that one valley has one sign of Berry curvature and the other valley has opposite Berry curvature. So the net result is, if I apply a charge current, so if I have a battery or something, I can only push the charge degree of freedom. So even though there's a valley degree of freedom, what the battery controls is and cannot discriminate between electrons of either spin or this other degree of freedom, which is the valley. So if you send a charge current here, existence of this term automatically deflects electrons belonging to one valley to one side, because the anomalous velocity for electrons of one valley is this way, and the anomalous velocity for the electrons belonging to the other valley is that way. So just a charge current here ensures that you get actually a valley current in this direction. So you'll get green sort of valley denoted here, K, will move in this direction, and an opposite current will have of the opposite value. So if you take any slice of this channel, you're basically getting a valley current, because one direction you're getting one kind of valley flowing, and the other direction you have other valley flowing. So that's the bulk valley transport because of the Berry curvature. If this is zero, there is no valley current in the system. And the detection also becomes easy. How do a voltmeter cannot tell the difference between a one valley or another, so it's actually non-trivial to detect it. One way to detect the presence of the valley current is to actually measure a voltage of, again, at this point, what happens is, if there is a pure valley current, because of the same reason, because of the same semi-classical equation, if there's a pure valley current in this direction, in the transverse direction, you are going to get a pure charge current. So if you send a charge current here, in this direction, there's a valley current, no charge flows in this direction, actually very, very little or close to no charge flows, then the valley current transduces a perpendicular charge current, and that can actually be detected by a voltmeter, and that's sort of how you detect that there is actually a valley current flowing in the system. So there have been some experiments looking at the flow of this valley current because of the Berry curvature, and I show this primarily for completeness, so people have looked at this aspect with some interest because of this electric field inducing a Berry curvature in the system by opening up a gap. And people have seen a Berry curvature because of this Moire unit cell being created, sort of like the Bragg scattering that happens at the Brillouin zone, mini Brillouin zone boundaries. And the system that we are interested in actually has both of these existing simultaneously in both the kind of sources of Berry curvature exist. So the way we experimentally detect it is we measure sort of two kind of responses of a device. So this is indicated in a schematic here. So this is geometry. This is the central channel, but you have these branches of it. So this is called a local geometry, which send a current on the outside. So charge current flows in this direction. And what we do is we measure a voltage drop across it. So this is what the kind of measurement that you would do conventionally to understand sort of electronic properties of any material. one other measurement that you can do, which is called the non-local measurement, which I already kind of alluded to in the last slide. You have the same geometry, but you send a charge current here, but you measure a voltage across down the line, either here, here, or even further. Okay, so this is called a non-local signal because charge current wants to if you think of this system as a network of resistor, wants to follow the shortest path to complete the loop, or least impedance. So for a charge current to flow via involving this, it's actually very, very little current flows through this part, and I'll show you that it drops exponentially as you go along this direction. But this non-local signal remains very strong because of the presence of this valley current. Because this valley degree of freedom, analogous to the spin degree of freedom, is being pushed in this direction. And these sort of two plots show essentially electrical measurements on the device. This is local, so these are where the gaps of the system are. The resistances are large. This is just essentially measuring the resistance. This is the non-local resistance measurement. So here it looks fairly uniform. It doesn't actually reflect the structure here that you see. It looks fairly uniform, but then it shows these structures at the gaps. And that's because the Berry curvature is actually only strong when you're sitting here. Everywhere else, the Berry curvature is actually vanishingly small. And you look at the slices of it, and the local electrical signal, which is a measure of the resistance, is, say, for example, blue. The non-local signal is comparable to the local signal. In fact, in certain regime, the non-local signal can be larger than the, which is very unusual and interesting. So you might say, okay, why is this happening? And the reason for that is very simple. It's this physics that I explained to you in the non-local geometry. Even though you send a charge current, you basically introduce a valley current in the transverse direction, and then some distance down, very long distance down, you again get an inverse conversion of the valley degree of freedom into charge degree of freedom, and then you can just connect a voltmeter and measure the voltage drop across it to find out whether there was a valley current. In the absence of Berry curvature being zero, you will not measure anything. It's actually very small. That's basically if I just try to look at what will be the local, what will be the ohmic contribution, that ohmic contribution actually drops exponentially. So if I look at the device geometry, and if I go some L by W ratio, so if I go 1, 2, 3, 4 squares down, then just the trivial ohmic contribution will actually drop by very rapidly, and it's actually very minuscule. So if you measure a signal, it has to be because of this additional degree of freedom, which is the valley degree of freedom. The valley degree also undergoes scattering, just like you would have electrons with a spin traveling down. There are scattering mechanisms which flip. Then this non-equilibrium flow of valley degree of freedom can actually decay. And as you go down further and further, one can actually experimentally measure sort of some reduction in the valley degree, current flow, and we can actually quantify it. So what we from this measurement, what we can, one of the things that we can do is we can get some idea about tuning of the Berry curvature. So as we apply an electric field perpendicular to the system, this non-local resistance, which is kind of a measure of the Berry curvature, it can actually be tuned. So you have a solid who's typically strain or kind of distorting the lattice is one way to tune the Berry curvature. Here, by applying a perpendicular electric field, you modify the electronic bands, and that basically reflects the modification in the Berry curvature of the system. So that's sort of very neat And that can be understood within a simple sort of toy model, which incorporates the modification of the flatness of the bands in some renormalized Fermi velocity, and one can see the Berry curvature distribution gets modified in K space. So this is actually pretty useful if one wants to make some devices or explore physics related to Berry curvature distribution in momentum space. So one additional sort of analysis that one can do, which shows hint of some physics which is not captured by this bulk valley flow. By bulk valley, I mean it's like a diffusive transport happening across the place where you inject a charge current. After that, there is a diffusive transport of the valley degree of freedom. There is, at very low temperatures, one sees some hint of deviation from this diffusive transport, and I'll point that out in a minute. So what we do is we try to understand that it's a diffusive transport by measuring sort of scaling relations, which allow us to, so there are some predictions. If it's a diffusive transport, then what should be the scaling between this non-local response of the system and the local response? So we measure this non-local response, and in this particular regime, which is a kind of small Hall angle is sort of the technical terminology for it. One can actually predict what is the value of the non-local resistance, and that actually it decays with some characteristic length scale, which is responsible for the essentially I told you different scattering mechanisms which scatter from one valley to another. So if one assumes this kind of one uses diffusive transport or assumes diffusive transport, this is the scaling that one expects, and we wanted to test that. So if there are resistance which depends on activated gaps, we can actually try to extract out measured gaps from different measurements, like the normal resistance, which is the local resistance, and non-local resistance, and ask what is the difference or the kind of ratio of the gaps measured, and that's sort of the measurement that we did. So this is there a question? I can hear some voice. Okay, if not, maybe I continue. Maybe somebody's audio is unmuted. So we measure the ratio of the gap, this gap that we measure by activated transport. So you can measure this quantity as a function of temperature and extract out this gap. And so this ratio as a function of electric field, which tunes the gap, we find it very close to 2. So this is a kind of a direct testing of the scaling relation. So if this scaling relation is correct for the diffusive transport, then this ratio of the gaps that we extract should be 3, and it's close to 3, some deviation. So this is the ratio of 3, of something close to 3 here. This is at this point in the parameter space of the system. So what we see is that it's very close to a bulk transport, but it actually has some deviations which could signal some interesting physics coming into play. And so what we try to do is we try to look at the scaling relation explicitly rather than through the gap. And what we find is that as one increases the temperature, you see a kind of scaling, which is the cubic scaling. So it basically says that at higher temperatures of about 50-60 Kelvin, which is in terms of energy scale, it's about 1/6 of room temperature. So about 4 MeV or 5 MeV, if you want to look at in terms of temperatures. You see a nice scaling, which is cubic, but at low temperatures, which is here, you see a deviation. And somewhat similar things are happening. We see there is some cubic-like scaling relation indicating that there is diffusive transport of this valley degree of freedom. But there is some deviation, and this actually at low temperature here, this deviation suggests some edge modes physics actually could be coming into picture. And there are some recent papers which seem to report the physics of the edge modes being formed at very low temperatures of about 30 millikelvin or so. But in the regime that we have looked at, there is indeed a Berry curvature. The Berry curvature deflects this valley degree, pure valley degree of freedom, and one can see it confirmed by these scaling relations. So I'm pretty much at the end of my talk. So the take-home message that we can see bulk valley diffusive transport. And at very low temperatures, we see some hints of deviation from this scaling, which suggests that the diffusive transport is no longer an accurate description. And so there could actually be ballistic channels, which are at the edges. These are called boundary modes, similar to the modes that I described when I was talking about Chern number. So there could be some topological character to these edge modes. That's something that's for some future work. So that brings me to the end. So this is sort of what I promised. I've told you about some basic things about the Berry physics and the connection to 2D materials, and how engineering the Berry curvature can happen because of layering and introducing a twist angle between them. And at the end, I showed you example of induced Berry curvature in this Moiré system leads to a valley degree of freedom, and the valley degree of freedom can actually be transported from one side to another by essentially a diffusive transport mechanism. All right, I thank you very much for your kind attention. I'm happy to take questions if you have any.
Thank you very much, Mandar, for the talk. Questions? Yes, there's a question by Geraldine. Yes, please, Geraldine.
Yeah.
Hello. No, it was just to thank you for the talk, which was very nice, but I had no specific question, sorry.
Okay, that's okay. Thanks.
Well, why someone raised the hand. I was so the last comment that you made on the possibility of non-diffusive anomalous transport is, so the local component, the local flow, this is always diffusive.
Yeah. So the charge is flowing diffusively. The charge has another kind of degree of freedom riding on it, which is spin or valley. So you send the charge current when you apply a voltage. The charge current diffusive through. It's not ballistic. Okay, and when it flows, it will generate. So one way to draw a cartoon, it pushes a kind of a wave of valley current on the side. There is no charge going with it, but it's a non-equilibrium population of this valley degree of freedom.
I see. But
so the charge, yeah, so the charge is diffusing through because of the Berry curvature. It sends out valley non-equilibrium flow on the side in the transverse direction.
I see. I see. I see. Another thing that wasn't very clear to me. So when you make all these twisted layers, so what you are looking for, or the interesting effects, happens when you have large Berry curvatures or when you have inhomogeneous ones? Well,
no.
What is more important?
A good question. So, so it's a so if I was just looking for like value transport, then I would want hotspots of Berry curvature which are large in magnitude because they give larger anomalous velocity. But homogeneous in K space probably doesn't really have much meaning. The homogeneity of the Berry curvature in the K space has no meaning because the electron packet, the electrons, when you populate in the bands, you have at different energies. So whether they're homogeneous or not, it doesn't matter. So for example, the Chern number, which is a kind of an integrated property of the band, it doesn't really care what is the inhomogeneity. So it depends on what physics one is looking at. If it looks patchy or kind of weird, for some physics, it doesn't really matter. It's the total, there are some other quantities which are of interest, which measure the distribution of the Berry curvature in the K space, like the moment of Berry curvature, which is called Berry curvature dipole. But in general, so Berry curvature dipole cares about how the Berry curvature is distributed in K space. But Chern number and Berry curvature per se don't care about whether it's homogeneous or not. Magnitude of Berry curvature can have an effect on determining how much of this anomalous velocity magnitude you have. So it's kind of an efficiency of could determine the efficiency of generation of the valley current. Does that answer your question?
Yes.
Okay.
Yes, thank you. Thank you. Any more questions? I don't see more questions. There was just a request from one of our young participants.
Sure.
They were wondering they were asking for a good reference for learning about Berry curvatures and Chern numbers.
Yeah, there's good books. If they just send me an email, I can send a couple of names.
Or maybe if you put on the chat.
Sure, I'll put it. Just
be helpful for them.
Yeah.
I learned it in Shankar's book of quantum mechanics,
yeah. So there are a couple of good new books. If you're sort of practitioner of solid state physics, there are some modern treatments of solid state. As I said, Kittel, if you look at it, the older editions don't really talk about this physics. But there are now basic solid state physics which incorporate this from chapter 1 or chapter 2 in a more cohesive manner. The name is blanking out, but I'll put the name here in a minute.
Very good. Thank you very much.
Sure.
Well, let's thank very much, Mandar.
Thank you. Yeah, I'm happy to be here. Bye.
Thank you very much. Thank you very much.